Okay. What we have learned so far is that we have 15 variables at each point in a continuum that we want to solve for. So for every point x at every time t, we need to solve for the displacements at each and every point. We want to solve for stresses, which is a second order tensor at each and every point. We need to solve for the strains, which are second order tensors at each and every point, and stresses, which are also second order tensors at each and every point. And this has three components, so it has three variables hidden inside it. This has nine components, but we know it's symmetric, so it has six independent components, and this we are not yet aware of. It is a second order tensor, so it has nine components. This is six. So this is nine components. We don't know anything much about it. However, we know that these two are related by what is known as the strain displacement relationship by this equation. So these two are related. It's a geometric relation. We have derived this from studying the geometry. However, we do not know what these nine components of stress are, the nine components of stress are capable of, what kind of laws these nine components of stress need to obey. So, uh, so this is where we start from. We are looking at enough number of equations. We are looking at enough number of equations in order to solve for all these variables. And right now, we have only these nine equations, out of which only six are independent. So we have six equations connecting displacement and strains, and we are looking for other equations that should be valid in order to solve for all these variables at each and every point in a body. So here's our usual potato. It has two parts. It's called V. The volume is called V, and the boundary is divided, as we had discussed before when we discussed strain, into two parts. One part is called delta Vt. One part is the rest of it, which is not delta Vt, and over delta Vt, tractions are applied, and we have already noted that concentrated forces like this are special cases of tractions. They are tractions with a delta function. Okay. And delta Vt is the part of the boundary over which tractions are applied. Delta V is the complete boundary. There can be body forces and there can be surface tractions applied on the body, and at every point, at any point x, in the body with respect to some coordinate system, with respect to some fixed coordinate system, at any point x, we need to find all these different variables. Now, we are going to see what are the laws that sigmas should satisfy. That is our goal in this part of the course. In order to do that, we will have to do a little bit of preliminary um, studies, and this is an important idea that I want you to understand. What I have done here is I have gouged out a part of this body and have named it omega. So omega is a part of V, omega is a subset of V, and its boundary is delta omega. Now, whenever we gouge out certain sections from bigger body, what we have to account for are the internal forces. So in this case, these are internal tractions. These tractions are internal tractions that were the tractions that the rest of the body was imposing on the body that I have, on the part of the body that I have gouged out. Its boundary is delta omega, and over delta omega, I need to now apply these internal forces in order to restore equilibrium. Of course, the B's are still applicable on this part of the volume, but the rest of the volume, uh, the rest of the boundary will have to have these internal forces applied, which are due to the fact that I have cut it out from a bigger volume. If I had cut it out from somewhere here, if I had cut it out from somewhere here, then parts of this tractions would also form, applied tractions would also form um, some part of the forces on the boundary of the subvolume. So the idea here is that if this this guy as a whole is in equilibrium, then any part of it, however small, is also in equilibrium. That's a basic idea of continuum mechanics, that no matter how small you go, you never see the atoms agitating about. You never see the discreteness of matter. You are always in a continuum system, so that body which is in equilibrium as a whole, any part of it, however small, is also in equilibrium. So this is where we start from, and we try to derive certain things called balance laws, which are basically expressions of basic physical laws. So these are expressions of basic physical laws, and these will be these will be needed much more when we do continuum mechanics later. But even for this course, we will particularly be interested in two conservation laws: conservation of linear momentum and conservation of angular momentum. Conservation of energy, entropy, etc., are also important, but not very important to us because of the limited scope of this course. However, there is one conservation law, which is the conservation of mass, which we will which in most of our cases will be trivially satisfied. I think in all of our cases that we deal with in this course will be trivially satisfied, but we still need to derive it in order to better understand the laws of conservation of linear momentum and angular momentum. So I will start with mass conservation. I will start with how we formulate these equations of mass conservation, and then move on to conservation of linear momentum and angular momentum. Okay.